All right, so we briefly addressed the concept of an energy diagram in one of the earlier videos. So I want to take just a few minutes more and talk about what we mean here. Energy diagrams are most useful when we're talking about conservation of mechanical energy. If you remember mechanical energy, we mean specifically the potential energy and kinetic energy of the system. So energy diagrams are useful when we can simplify our conservation of energy to be just the initial potential and kinetic energy of the system is equal to the final potential and kinetic, the sum of those. So for example, I brought it up earlier when we talked about tossing a ball in the air. We throw a ball, if it leaves our hand with the speed vi, goes up, slows down, eventually it reaches a maximum height where v is 0, and then of course the ball speeds up, coming back down. And by the time it gets back to the same level at which it was thrown, this V final would equal V initial. So to represent on the energy diagram, what we mean by that is energy on the vertical axis and position or height in this case on the the horizontal axis. We know in this specific example, if I went ahead and just said, hey, you know what, let's call y equals 0, this location where the ball is leaving my hand, all of the energy initially would be kinetic. We're essentially defining potential energy initially as 0 by saying y is 0 there. As the ball moves upwards, at any given point in between leaving my hand and maximum height, the ball will have some potential energy and some kinetic energy. Here, it would have some potential energy and some kinetic. The amounts of individual potential energy and individual kinetic energy would be changing, but the sum of those two, adding them up at any one given point in time, has to equal the same value, the same number of joules all of the time. At the highest point, all of the energy is potential. None of it is kinetic. And so an energy diagram can represent this. We can represent the potential energy, mgy, by a vertical line, right? At any given moment, the potential energy this ball would have depends on its height at that moment. We could mark that at any point. Any given amount of potential energy means a specific height value. Now, eventually, we would have a maximum height value right here, where this intersects represents the total energy in the system. So the rest of this line that I drew for gravitational potential energy, that theoretically the potential energy can get bigger and bigger and bigger. But in any one given situation, the ball's going to reach a specific maximum height. And as we mentioned, at that moment, the kinetic energy has to be 0. And by total energy, we mean potential plus kinetic. So if at that moment the kinetic energy is 0, it's all potential. So this line still represents the gravitational potential energy in the system. But because my potential energy graph, that line at an angle that I drew to represent mgy, because that intersects the total energy, that is the maximum height. This we call a turning point, which hopefully makes sense. If we think in terms of the ball itself, it gets up to its maximum height, the speed is 0 for an instant, and then the ball heads back down, and it speeds up going back down. On an energy diagram, anything from the horizontal axis measured upwards represents this value at the moment we're talking about. So that represents the potential energy the ball has at any given moment in time. A nice thing, too, is if we measure the rest of the way, so from the potential energy line up to the total energy line, this represents the kinetic energy the ball has at those moments in time. So up here at the turning point, we're saying kinetic energy is 0. Down here at the bottom, the kinetic energy is max, and the potential energy is 0, because the potential energy line is intersecting the origin. So in these graphs, we can easily, just in a picture, relate potential energy and kinetic energy together. Now, one other thing from this, we know gravitational potential energy is a way to talk about the energy in the system because of the force of gravity. We know the force of gravity points downwards with a magnitude of mg. So negative j hat is the direction, mg, the mass, 9.8, that determines how big the force is. When we look at gravitational potential energy, mgy, it turns out, since this is a line, if you remember the equation of a line, generic equation, y equals mx plus b, y on this graph is energy, x on this graph is height. The slope then has a specific meaning. This graph, there is no y-intercept for the potential, well, the y-intercept is 0, I should say. So if I am relating u to mgy, my slope represents mg. The slope represents the magnitude of the force. But the force is downwards. It turns out when we are dealing with potential energy, I don't know if you happen to remember, we know the work done by any individual force generically can be written as the integral of the force dotted with displacement. And in terms of potential energy for gravity, that ends up equaling the negative change in potential energy. So by integrating force, we can get to a change in potential energy, but it turns out the opposite is true. If we take the derivative of the potential energy with respect to position, we get the opposite, but meaning direction of the force. Now, in terms of gravity, it is just, we know gravity is only causing a speed up or slow down when the object moves vertically. So we would technically say this ds is really dy because the object needs to be moving vertically. Ultimately, since we have a graph of energy per height, the slope of that graph represents the opposite direction, but the magnitude of the force. That is unique. That's a unique relationship for potential energy and the force that we are describing the potential energy interactions with. So that applies to force of gravity, but it would also apply to a spring. So quick jump to a spring. We already know the force that a spring exerts is opposite in direction to the displacement of the spring. K is the spring constant. We know the potential energy in a system because of the stretch of a spring or compression of a spring technically is delta S. I've been writing it as just S because I have been defining my equilibrium position as an S equals 0. So if I were to graph an energy versus S, this S equals 0 would represent the equilibrium location of the spring, meaning the spring is not compressed or stretched. I know the energy of the spring would be, oh, sorry, that's not what I wanted. Sorry, there's more abilities apparently than I realized, and I accidentally used one. Okay, so if S is 0, this spring has no energy. I know if the spring is compressed, the energy gets bigger and bigger, but it's parabolic because the energy the spring has is related to S squared. So my potential energy of the spring increases, it gets bigger and bigger, and it does so parabolically. But the same is true if the spring is stretched. It increases parabolically. How much the spring is compressed by determines how much energy it has. So for example, if the spring is compressed this distance, then it has this energy. If the spring is, stretched this distance, then it has this much energy. And so forth. The total energy line, so remember, we're talking just mechanical energy. The total energy at any given moment, because we're assuming just the spring here, that has to be constant. So there's some line here where I draw it would represent the total energy. That value corresponds to a maximum stretch. So the most that spring has been stretched out is what is determining that total energy. The same would be true if we were compressing a spring. If I drew a line down from that intersection, this would represent a maximum compression. So the total energy line is determined ultimately by how far the spring is compressed or stretched totally. At any location, measuring from the horizontal axis up is the potential energy. Measuring the rest of the way would be the kinetic energy. These points where the total energy intersects the potential energy, So if my total energy is where I just drew it, I don't need the rest of the potential energy line. That's for a different story. Theoretically, the spring can have more energy. But in any one given situation, the spring has a maximum amount of compression or stretching. So where the total energy line intersects the potential energy line, just like with gravity, that is called a turning point. And that's because all of the energy is in the spring, the interaction between the spring and the mass attached to it, and no energy is kinetic. So that's the point. If the mass had been on the spring, sliding to the right, it stops, and then the spring pulls it back. So turning point, we literally mean it was traveling one direction and now it's going to head back in the opposite direction. Where on this graph the potential energy is 0, all the energy is kinetic. So these graphs can give us an idea and a relationship, a way to look at the conservation of mechanical energy. If you remember in the last situation with gravity, I said that we could find the force, or the opposite of the force was the derivative of the potential energy. Or the derivative of the potential energy with respect to position is the opposite of the force. Doesn't matter which direction we put the negative sign on. This still means that if we look at the slope of this potential energy versus position graph, that slope will tell us the force at any given moment. So when we're on this left side representing compression, the slope of the tangent line is positive and it's getting smaller and smaller, meaning the force is a smaller magnitude as that S gets to 0, as we get closer to the equilibrium state. But the slope represents the opposite of the force. So here the slope is positive. That means the force is negative. It's opposite the compression. So if the spring was compressed to the left, the force is to the right. So that negative really is explaining the negative sign in Hooke's law here. Just that the force the spring exerts on an object is always opposite in direction to the compression or stretch of the spring.